Okay, thank you very much. Now we have the last presentation-only paper before the lunch break, which is called LocuNet, Fast Urban Positioning Using Radio Maps and Deep Learning. And maybe it can also answer the question how you get a good initial starting point. The presentation will be contributed over Zoom. Can you
Hi
hear
everyone, thanks for having me here. Can you hear me well?
Yes, we can hear you, but there's some noise, so if you can maybe go closer to the microphone or something.
Is it better now?
Yeah, I think it's okay. Thank you very much.
Okay, I think I will start anyway. So, should I share my screen or can
Yes, please share your screen for the slides if that's possible.
Okay.
Okay, we can see your slides.
Great.
Perfect. Thank you.
Thanks for having me here. So, the title of our paper is LocuNet, Fast Urban Positioning Using Radio Maps and Deep Learning, and this paper was originally presented at ICASP 2022. This is joint work with Ron Levy, now at Teknion, Gita Kutniok at LMU Munich, and with Giuseppe Caire at the Technical University of Berlin. So as you know, that the localization is a quite important problem with many applications in many different fields, and the GNSS is not a viable option in urban scenarios due to the blockage by the buildings or the cars or all the people in the environment. So one needs to come up with other solutions actually to have good accuracy in an urban environment. So one option is using the received signal strength, which is available in most of the mobile devices. That is very common operation used in the very fundamental operations in wireless networks. And there are also other options which are again based on using the wireless signals, such as using the time of arrival or TDOA or the angle-based methods. But these methods require additional hardware, unlike the RSS option, where it is just common available at every device, but for other options, one would need additional hardware. So our method is based on purely on the received signal strength. And for this, one can make use of any wireless signal source with known location. That can be the base stations or Wi-Fi points. Important is to know their locations such that we can use the radio map estimations, that having them as the transmitter. But generating such radio maps are not a very easy task. For this, to have high accuracy, one would usually go for using a ray tracing software, but such calculations would take lots of time. So it is difficult to use such high accuracy simulations in real time. But recently, with recent developments, also due to our previous work, which was called Radio Unit, one can achieve such estimations, radio map estimations, in much shorter time. So our studies show that our method LocuNet can achieve state-of-the-art localization performance with comparison to RSS-based methods or time of arrival ranging-based algorithms that we compared with. And for this also, to make such comparisons, we have generated two novel data sets by using a ray tracing software called WinPro. And I guess also this is, to the best of our knowledge, the first work that shows these comparisons in a realistic urban environment. So here is a description of the datasets that we proposed. The first one is called radiologs here. Here we have the RSS maps, these signal strength maps. And the second one is, as its name suggests, it is about the time of arrival values, which is like how much time it takes from the transmitter, the base station, to the receiver points. And this is based on the dominant ray, by taking into account only the dominant ray, which is the shortest free space path. And in the longer version of our paper, which is on arXiv, one can find more details about the datasets as well. So to assess the performance of our method, we considered 3 different scenarios to study the effect of discrepancy between what one can have as the radio map estimations and what would be the real measurements, because there's going to be a discrepancy. Even how good your estimation of the environment, there is always going to be some sort of mismatch between how you model the signal strength or time of arrival, everything. So because the difference between the real life and what you can calculate. So the first one is very optimistic scenario, where we assume that we have the exact match, that we have a model of the environment, the propagation environment, and we can also calculate this with very high accuracy. And there is only a small problem due to that we are using an estimation method. So this is like inevitable mismatch between how good your model is. There is still going to be some sort of mismatch. In the second one, we consider having different models, that the propagation in the real life is governed by some method, but we can calculate it through another method. And the third one is the most realistic one, because there we additionally also consider the presence of additional obstructions in the environment. So this is actually something very important, because it's inevitable. In an urban environment, there are going to be cars, the environment is going to change all the time, so there is no way that you can calculate such radio maps. There is going to be a mismatch because of the cars. This one is the most realistic one. So here we see the histogram of the differences of these different considerations. So our method is a unit variant, and in the last year we are taking the center of mass, and the layer before it represents a heat map or posterior distribution. So together with this, we are taking the mean of the posterior distribution in a way. So actually, one interesting thing is that we noticed by allowing for negative values at this heat map, we got better results than forcing the heat map to be non-negative. So because of this, then we instead of calling this heat map, we call it a quasi-heat map, because it takes the negative values as well. And the log unit takes these inputs as these are obligatory inputs that one needs the path loss measurements, and one also needs the by path loss I mean also the receive signal strength, related. If you know the transmitter power, then knowing the pathos, then you know the signal strength, receive signal strength. And besides this, one also uses the estimated radio maps. So here's an example of using the dominant path model. We consider two models to model the mismatch between the reality and the estimations. And this would be the estimation of the dominant path model with the radio unit that we use to accelerate the calculations. As you see, it is quite good estimation. And this would be the third scenario that we have studied here. The real life simulations, the surrogate that we are using for real life is another model, and there are cars in the environment, which makes it quite different than this would be the estimation that we are using, and this would be where the measurements assumed to come from. So here is a visualization of the heat map that, as I mentioned, we called it quasi-heat map because it has positive and negative parts. This would be the positive part, the negative part. And for the third scenario, we observe actually now the localization actually is more determined by the negative heat map, which is quite interesting. And here are the results, the numerical results. We compared with the KNN method for the three scenarios, and we observe that in each scenario, LockUnit outperforms compared methods, especially in the most realistic situation where the cars are present and there is additionally the model mismatch. And here is a comparison with the time of arrival ranging based methods. Here also we observe under several settings that the noiseless case, which is very optimistic for both of the methods, and these are the methods that we compared, the theory ranging based methods, and also under the noisy setting. So to sum up, we observe that the proposed method can reach state-of-the-art localization accuracy, and also compared with RSS-based methods and also with time of arrival ranging-based methods. And due to the accelerated radio map estimations, it can be suitable for real-time applications. And we are presenting two novel data sets which allows for comparison of RSS fingerprint and time of arrival ranging based methods, that other researchers can also use this data set to test their methods. I think that is all. Yes, you can find a long version of this work on arXiv. We have our data sets available on project homepage. Also, we recently uploaded the data set with some better explanation on IEEE Dataport. Our code is also publicly available, and this concludes my talk. Thank you.
Thank you very much for the talk. Super interesting. If there's any questions in the audience, please raise your hand. And I maybe start with a first quick question. Have you ever considered this task of localizing from radio signal strength in a temporal domain, so that maybe you get some odometry from another sensor and then you get multiple readings of signal strength? Or is that up for future work?
I'm sorry, can you repeat? Did you say the temporary, you mean taking into account a time series? samples.
Yes, exactly. A time series and maybe like the positions between them from the odometry from a car or something similar.
No, this we considered on a very simple setting without utilizing any further information, but incorporating such information would be definitely useful, or conversely, that our method could be perhaps adapted to such methods.
Okay, thank you very much. Now there is a question from the audience.
Hi, my question is probably complementary to the first one. From your experience, how much do radio maps in real settings, real urban settings, change over time? Days, months? How practical is it to use in real scenarios once you build a radio map for a certain environment?
Thank you for the question. So I think one can update the radio maps by somehow incorporating changes in the environment. Actually, even the changes in the weather, like whether it is raining or not, everything can change the radio map, the propagation environment. But the robustness is more important, and we believe that our method is robust for such changes in the environment, because we considered also having different propagation models or presence of objects in the environment which are very big changes. So actually there is no way that one can always keep the track of the environment. So one needs to have a robust model, and we believe actually we have exactly addressed this issue.
Okay, thank you very much. Thank you again for the talk. It was really interesting, and thank you all for your questions.